Okay, good morning, everyone. So last time we had worked out the formulas for first order perturbation theory for stationary states, and today we're going to do some examples. So the first example is going to be a particle in a box with side L, and we're going to have a perturbation which is going to be a potential that we add to the middle of the box, which is going to be height V0 and width of A. So the picture of the potential that we're adding, or the total potential that we have, is it's infinite at the sides of the box and outside the box. There's this bump in the middle, V0. This is minus A over 2 to A over 2. And then it does this. So minus L over 2 to L over 2. This is the forbidden region, completely forbidden region. And so the perturbation that we're adding, I guess we called it W, we're calling it W, and we're going to work in position space. So W of x is going to be V0 for absolute value of x less than A over 2. And it's going to be 0 for absolute value of x greater than A over 2. Okay, so in any perturbation theory problem, the first step is you have to identify the eigenenergies and eigenstates of the unperturbed problem. So I'll write here, unperturbed problem. And fortunately, we've already done that in section 5.4 of the notes. Okay, and so the unperturbed energies, which I remind you, we use the curly E letter for unperturbed energies, are equal to h bar squared over 2m times n times pi over L squared. And this is for any integer n, as long as it's greater than 0. Okay, and then the wave functions, which tell us the kets, are depending on whether n is odd or even. So first for n odd, I'm going to use phi for my unperturbed wave function. This is the same thing as the inner product of the position eigenstate x with the state n. And reminder, that's square root of 2 over L cosine of n pi x over L. This is only if n is odd. And for n even, it's exactly the same, except it's a sine instead of a cosine. Okay, so that's for n is 2, 4, 6. Okay, and so all of this is the data that we need, or the results that we need for the unperturbed problem. And now we can go ahead and calculate the perturbed energies. And so the correction to the energy of the nth state at first order in perturbation theory, that's the superscript. Remember, that was this formula. You just take the expectation value of the perturbation Hamiltonian in the state that you're interested in. And in position space, that means we're going to do the following integral. We're going to integrate minus L over 2 to L over 2 dx of the wave function phi sub n of x, that's the unperturbed wave function, multiplied by the perturbation Hamiltonian But now we get to use the fact that the perturbation vanishes unless x is closer than a over 2, according to our potential up here. And so really there we can rewrite the integral instead as integral from minus a over 2 to a over 2 dx phi n squared. And then we can just put v0 there, because within that range, the potential is just equal to v0. Okay, so rather than do this for a general case, what I'm going to do is evaluate this for the ground state. And then for homework, you get to do the first excited state. So you just have to figure out what changes for the first excited state compared to the ground state. So for n equals 1, that's the ground state. The first order correction to the energy is v0 is just a constant, so we can pull it out of the integral. There's also a, if we go back up here, there's a square root of 2 over L, which is going to get squared, and there's a cosine that's going to get squared. All right, so let me write my 2 over L, integral minus a over 2 to a over 2 dx. And then what goes here is cosine squared pi x over L. And that's not too hard of an integral, so the answer turns out to be v0 times a over L plus 1 over pi sine of a pi over L. Okay, and so then we can summarize what the ground state energy is. It's just the unperturbed value, which looks like h bar squared pi squared over 2ml squared, plus something proportional to the perturbation, which turns out, I'm just recopying the line above. It looks like this. Okay, so when having done a problem, it's always a good idea at the end of doing a problem to just check it by plugging in some extreme limits, just to make sure. So one extreme limit that you can plug in is, what if a equals 0? So if I plug in a equals 0, that means I didn't put in any perturbation Hamiltonian at all. And then the correction is indeed 0. So that's a particularly silly limit. Another limit you can plug in is, what if a was equal to L? So if a was equal to L, and we go back to our potential up here, that just means we're adding in a bump that actually covers the whole thing. And so we've just shifted our energy up by v0. And sure enough, if we look at this expression, if we plug in a equals L, the sign is going to be sine of pi, which is 0. And this is going to be 1. And so in that case, sure enough, E1 of 1 is equal to V0. We just shifted the energy up by an exact amount V0. And so not only is this good at first order in perturbation theory, it must be true at all orders in perturbation theory, although we're not going to evaluate that directly. Okay, so that's the first order correction to the energy. Usually wave functions are a little bit harder, so let's go ahead and do the wave function correction. So for the wave function, so what we really need is we need the matrix element of a general state J with the correction to the state, psi 1 of 1. Again, we're just doing the ground state here. And so if you look back at the formula for that, it's 1 over the unperturbed energy of the state we're talking about, which in this case is the ground state, minus the energy of the state J, times the matrix element of the perturbation Hamiltonian. Okay, so in general, that's what we would need to evaluate. So let's go ahead and do it. So let's do the energy denominator first. So the energy denominator, we just look back up above and we see that's h bar squared over 2m. Both E1 and EJ have a factor of pi squared over L squared. And then there's a factor of 1 for the ground state minus J squared for the jth state. Okay, so now we need to do the matrix element, which is V0. We have to integrate from minus A over 2 to A over 2, just as we did before. And just as we did before, there's a factor of 2 over L, because there's square root of 2 over L in front of each wave function. And then there's a cosine J pi x over L for the jth state, and a cosine of pi x over L for the ground state. Okay, now this is actually only good for J odd. And the reason is because, remember, if J is even, then I shouldn't be writing a cosine down here. I should be writing a sine function instead. So that's okay. We'll just have to come back to the J equals even case. But first, okay, we need to evaluate that integral. And so this is, let me write all my constants in front. Okay, and then there's a 2 over, it turns out there's a 2 over pi. And the integral looks like this, sine pi a j minus 1 over 2L over j minus 1. But wait, there's more, plus sine pi a j plus 1 over 2L divided by j plus 1. Okay, so this is not a class in doing integrals, so I'm not going to explain how one does that integral. And on your homework, it's fair game to use some other software that you might have at your disposal to do the integrals. There's nothing particularly elegant or pretty about this, but that's the answer. So that was for J odd, and now we have to go back for J even. So for J even, then we're going to have instead this integral, minus a over 2 to a over 2 dx sine j pi x over L cosine pi x over L. Okay, and that turns out to just be 0. So why is that? That's because we're multiplying together an odd function of x times an even function of x, and then we're integrating over an even interval in x, and so the contribution from negative x cancels the contribution from positive x. Okay, just because the sine function is odd and everything else in this is even. So in quantum mechanics, we say the same mathematical fact is due to the parity selection rule. So this is the parity selection rule in action. Okay, and so it's worthwhile saying how that works in general terms rather than for this specific case, because it might be less obvious in some other cases. It's not too hard to see just from this integral why it's happening. But let's remember how the parity selection rule works. So recall, let's say, so there's a big if here. Let's say the following things are all true. that the parity operator acting on another operator A times the parity operator again is some number pi sub A times the operator A. And let's say that the parity operator acting on a state psi is some eigenvalue acting on that same state. And let's say on another state, we'll call it phi. Let's say phi is also an eigenstate of the parity operator. So one thing we learned when we studied the parity operator is for that to be true, those eigenvalues little pi have to be plus or minus 1. So if this is true, then these are plus or minus 1. Now, it's important to note that it doesn't have to be true that just any old state is a parity eigenstate. In fact, it may not be true. So that's the reason for the big if. You just can't apply this unless you have parity eigenstates, as I've written there. Okay, so, but if those are true, then it's true that the matrix element phi a pi, or phi a psi, I should say, is 0 if the product of those eigenvalues is -1. Of course, it has to be either -1 or +1. If it's +1, you don't learn anything. But if it's -1, then it says that the matrix element is 0. Okay, and so that's really what we saw in this example for even j. Okay, so that means we've done even j and we've done odd j. And so now what we've got is the first order correction to the wave function. I'm working in position space here, is equal to a sum over all j's, except that we're not supposed to sum over the state we're in. There was always this does not equal to in the summation. So we're not summing over j equals 1. And we don't have to sum over j equals even because they were 0. And so in this case, we're just summing over odd integers that are greater than 1. And now we just need to plug in all of the stuff that we calculated, which is 4m v0 L squared over h bar squared pi cubed 1 minus j squared. And then there was our ugly trigonometric functions. Okay, and sine pi a j plus 1 over 2l over j plus 1. And I see that I've completely run out of space, but there's more, because what gets multiplied here is the wave function for the jth state. Okay, and that's not a very good pi. Let me rewrite my pi here. Okay, and so that's the correction to the first order correction to the ground state wave function. It's there as an infinite sum in this case. And so in general, if you're applying this in the real world, not that this is a particularly real world example, but you can expect to find things like infinite sums for the wave function, even at first order in perturbation theory. Okay, and so now that you've got that, then the complete wave function of the ground state is the unperturbed part. Oops, I don't want an n there because n is 1. Plus that mess that I just wrote on the line above it. Okay, so all that's up here. this whole thing. Okay, and notice once again that this is equal to 0 if A equals L. Okay, so if A equals L, then all we've done is we've taken the potential and we've shifted it up by a constant amount. That's going to affect the energy eigenvalues, but not the energy eigenstates. And so sure enough, it's good to see that when we plug in up here, if we plug in A equals L, then nothing happens to the states. Okay, so that's it for this example. As I said, for homework, you're going to just get to do the exercise of doing the n equals 2 state. Okay, and so what you're specifically supposed to calculate is the first order correction to the n equals 2 state energy and the wave function. Okay, and if you're guessing that what happens is mostly that some sines turn into cosines, that's exactly what should happen. All right, any questions on that?
I have a quick question.
Yeah.
So when distinguishing between the j and the nth states, so like I know we put for the expectation value of the perturbation, we have j and 1 on one side. So that's for the first state and the jth state. But how do we reconcile the j states? I'm kind of confused when we go to calculate that.
How do we reconcile the j states?
Yeah, so like when we took there you have j or broad j w ket 1. So if we're in the second state for like the homework, right, the ket will be 2 there, but j I'm confused about what exactly we use for j since the sum goes to infinity.
Right. So in this example, what we're really going to be doing is that we're going to be applying this for general j. And so in principle, we should evaluate this for every j, every integer j. And then we're going to be summing over all j's. Right. So in principle, you have to do it for every j. Here I split it up into j odd and then even j. But in general, you have to do both. And then you have to do this infinite sum. Some of the terms in there will vanish, just like in this example. So in this example, what we ended up with when we had to do the sum is we ended up only having to include 3, 5, 7, 9, 11, blah, blah, blah. And so you should think about, by the way, which j's will appear when you do the n equals 2 state.
Okay, so when I'm handwriting down this correction, how many j's is good enough, essentially? Kind of like how we only take second order.
Right, so that's a good point. So notice that a good thing is happening here in this infinite sum is that you've got a 1 minus j, oops, my pen spontaneously decides to erase sometimes. So you've got a 1 minus j squared in the denominator, and then there's also a j minus 1 in the denominator and a j plus 1 in the denominator. And so that means when you go to pretty large j, these terms are going to get small pretty fast. And so it depends how accurate you want to be to know how many terms in j you actually have to keep, let's say if you were doing this on a computer. But the good news is that for any given accuracy that you desire, if you go to sufficiently large j, this is going to get better and better because of the j's in the denominator. Right? There's also the signs involving j's in the numerator, but those are trigonometric functions. They're bounded between -1 and 1. So in general, things will get better at larger j. And so eventually, depending on how accurate you might want to be, you could keep j up to 10 or maybe j up to 100. But in general, sufficiently large number of j's will be good enough.
All right, thanks. That really helps clear it up.
Sure. Other questions? All right, so let's do another example. And this is a little bit more of a practical example. And this is the effect of the proton size. And by size, I mean real physical size, not mass, That's a different statement. So on the hydrogen atom, energies. So in this case, we're not even going to worry about the wave function. We're just going to be interested in what it does to the hydrogen atom energies. Okay, so to model this, so remember that up to now, what we had done is we had treated the hydrogen atom nucleus, namely the proton, as a point. Okay, and so if there's my proton, we know the electrostatic potential is equal to the proton charge in appropriate units, which we call E, divided by R. And the electric field for that is E over R squared times the unit vector in the radial direction R hat. But now what we're going to do is we're going to treat the proton as, and this is not exactly a true statement, but we're just trying to illustrate the idea. We're going to treat the proton as a uniform charge density ball. Now, what I'm going to show you is you could model the proton charge density a little bit more realistically as sort of a Gaussian or some other fuzzy function rather than just being a uniform charge density ball. The same method will work. So here's our proton picture now, and we're going to say the radius of that is A sub p, which is the radius of the proton. And I'll put that in quotes because, again, that's not particularly realistic. All right, so what we need to do first is figure out, given that model for the proton, what does the electrostatic potential look like that the electron is going to be moving in? So I'm going to take a little detour and not do quantum mechanics for a moment, for a few minutes, and instead do electrodynamics or electrostatics. So we want the electric field first inside the proton. Okay, and so we use Gauss's law, which says if we do an integral of the electric field dotted into the area element at a fixed radius, so we're integrating over a sphere, that should equal the charge enclosed divided by the permittivity of free space. And so let's evaluate both sides of that equation. By symmetry, the electric field dotted into the area element, which is the radial direction pointed out, is just equal to the area of that sphere. The area of a sphere is 4 pi r squared. And the magnitude of the electric field is the radial component. And on the right-hand side, we have the charge enclosed in a sphere is the volume, 4/3 pi r cubed, times the density, the charge density. And remember up here, we decided to say it was a uniform charge density. So whatever it is, it's a constant. And then we can't forget to divide by our permittivity of free space. Okay, and so if we solve that, that's going to tell us that the radial component of the electric field is R over 3 times our charge density divided by epsilon naught. Okay, and so now what we need to know is what is rho? What is this charge density? Okay, and we can work that out because we know the total charge on the proton. Okay, another way of doing it is to say that when the radius is the charge of the proton, we know that the electric field is equal to E over R squared, because it's the same as if the proton were a point charge. Once you're outside the radius of the proton, it looks just like a point charge. Okay, so that means that it must be true that E over the proton radius squared is equal to, comparing to this, that must mean that it's equal to the proton radius divided by 3 times our charge density divided by the permittivity of free space, which says the charge density is 3 permittivity of free space, charge of the proton over the proton radius cubed. Okay, and so now we know inside the proton what is the electric field. Namely, it's linear in the radial coordinate, and it's divided by the proton radius cubed times its charge. All right, so let's just make a graph of what we've learned there. Well, actually including also the electric field outside. So we've learned that outside the proton, it does the usual thing. It's E over R squared for R greater than or equal to a proton. And it's ER over a proton cubed for R less than or equal to a proton. And so if we were to just graph what the electric field looks like as a function of radius, here's the proton radius. This is the electric field. Okay, and so it's rising linearly. And then once you get outside the proton, then it falls quadratically. Okay, so that's what the electric field looks like. And our whole purpose in deriving that is, given the electric field, now we can figure out what the electric potential is. The electric potential is what's going to go into the Hamiltonian. Okay, so let's do that. We'll do it first inside the proton. Okay, so the electric potential, which I'm going to call phi, is equal to the value at the surface of the proton minus, there's this annoying minus sign in the definition of the potential, the integral from the proton radius to the value R that you're interested in of the electric field dotted into the length element. So that's ER times dr. Okay, and so now we just need to take that electric field and integrate it. This is going to equal E over a proton, that's from here, minus integral a proton to R, ER over a proton cubed, dr. So this is E over a proton minus E over a proton cubed, R squared minus a proton squared, all divided by 2. All right, so now we've got the electric potential because that actually simplifies a little bit. This can be written as just 3 over 2 a proton minus R squared over 2 a proton cubed times the electric charge. Okay, quick sanity check. The potential should go like charge over distance. And so units, this is indeed 1 over a distance. This is a distance squared over a distance cubed. So that's also a 1 over distance. So everything looks good. And now once we have the electrostatic potential, that tells us that the electrostatic energy of the electron is minus E, because the electron has charge minus E, times phi of R. So this is minus E squared over, let's write it like this, E squared over 2, 3 over a proton minus R squared over a proton cubed. Okay, so that's what should have gone in the Hamiltonian for r less than the proton radius. And so now we can make another graph, another sketch of what does v of r look like as a function of radius. And it's negative, notice. Here's where I'm going to mark off the proton radius. And so it goes like -1 over r when you're outside. So this is minus e squared over r. And then once you're inside, if we look at this function right here, this is a quadratic function. It's not blowing up. Instead, it's looking like this. Okay, and what it would have looked like, or what it did look like in the previous approximation that we did last semester, is this goes off to -infinity. So this is certainly more realistic than what we'd done before, right? Because the proton does have some finite size. And so the perturbation is existing in this region. So in this region, I'm going to write the change in the potential energy. This is also known as the perturbation. So in general terms, this is what we were calling W. And it's just the difference between what we actually have, -3 e squared over 2a proton, plus e squared r squared over 2a proton cubed, minus what it was if we didn't include the proton size. Okay, and so this is the unperturbed part. Okay, and this perturbation exists only for 0 less than r less than a proton. If you're outside the proton, nothing changes. Okay, so all of that was just classical physics, and our goal here was just to find out what the perturbation Hamiltonian was. This is it. And so now, working to first order in perturbation theory, we use our great formula, which says, and we're only going to do this for the ground state, that the ground state, which is 1, 0, 0. So when I write 1, 0, 0, that's the n, l, and m quantum numbers. The 1 here is telling you that we're doing first order in perturbation theory. And this is the matrix element 1, 0, 0 times our W, which is delta V, times 1, 0, 0. All right, so we just have to evaluate that, and we're going to be working.
I'm sorry, so I just wanted to get this.
Sorry, go ahead.
Yeah, I'm sorry. Just so basically that dotted line, the dash, that's what the perturbation is, correct?
No, so the perturbation is, let me annotate this a little bit further. So this is just the old potential, not including the proton radius. Okay, and so what the perturbation is it's the difference between the dashed line and the solid line. That's the perturbation. Okay,
Okay, thank you.
Black solid line is our new model for what the proton potential is. The blue dashed line is the old model, and the difference is the perturbation. Okay, so that's in fact what this is. Good, other questions?
I had a quick question.
Yeah, sure.
When you started writing about the inside proton, you wrote, I think it's psi of r equals, yeah, right there at the top, inside proton. So I was kind of confused where that first equation kind of came from.
Ah, right. So here we're using the general fact that the potential, the electrostatic potential at any position, I'm going to write this in a very general way. the electrostatic potential at any position is equal to the electrostatic potential at any other position minus the integral of E dot dl from, sorry, I should put here R0 to R. Okay, so that's just the formula for the electrostatic potential from electrostatics. Okay, and now what we're doing is we're saying we know what the potential is at the surface of the proton here, because that's the same as it would be if the proton didn't have any radius. It's E over a proton, which is what I wrote here. Okay, and then this part is just the integral that tells you what the electrostatic potential is in terms of the electric field. Okay?
All right, sounds good. Thank you.
Sure. All right. So all that was just classical review of classical electrostatics. All right. So now we've boiled it down to evaluating this matrix element. And now we're going to just work in position space. So we're going to be integrating. The perturbation only exists within the proton. So we're going to be integrating 0 to a sub p dr 4 pi r squared. So all of this is the volume element. And when we do the angular integration, that just gives us the 4 pi because everything is spherically symmetric. Okay, and next point is to put in the Bra and Ket wave functions, which fortunately in this case are just the hydrogen atom ground state wave functions. So each one of them looks like this. Okay, but there are two of them. So we square it. And then we plug in our delta V, which in this case is otherwise known as W. And so this is minus 3 E squared over 2a proton plus E squared R squared over 2a proton cubed plus E squared over R. And if I were smarter, I would have factored out an E squared right away. Okay, so that's the integral we need to do. Let's just rewrite it by pulling out all the constants. There's 4 E squared over a0 cubed. Our pi's actually cancel. And then what we're left with is this integral. Okay, we have two factors of e to the minus 2r over a0. And then what's left over is again this stuff. Okay, so we have to do that integral. Now, this integral is not that hard to do, but it's actually even easier to notice that we can approximate it to a very, very high precision. Because if you are inside the proton, which is very small, then this factor of e to the minus 2r over the Bohr radius, which is much, much, much larger, is going to be essentially always equal to 1. Okay, r over a0 is going to be much, much less than 1 when r is between 0 and a proton. So it does no harm whatsoever to just replace that factor by 1. And then the integral gets even easier. And the whole thing works out to be, according to me, a proton squared over 10. Okay, you're just integrating a polynomial. And so if we put all that together, we get twice the electron charge squared, a proton squared over 5 Bohr radius cubed. Okay, so that's the correction to the ground state energy based on the fact that the proton has a finite size. And to put this into real number terms, recall that e squared over 2 Bohr radius is 1 Rydberg. which in energy, which is equal to 13.6 electron volts. If you know nothing else about the hydrogen atom and quantum mechanics, that's the number you should know. And so that means our first order correction to the energy is 4/5 times proton radius squared over Bohr radius squared in Rydbergs. Now let's plug in the actual numbers. The Bohr radius is about 5.3 times 10 to the minus 11 meters. The proton radius is, roughly speaking, we're just trying to get an idea of the numbers here. It's about 9 times 10 to the minus 16 meters. Okay, which is otherwise known as 0.9 femtometers. And so you plug that in and you find out the shift in the energy due to the proton having a finite size is 2.3 times 10 to the minus 10 Rydbergs. So the moral of the story is that it was actually a really, really good approximation to ignore the proton size, because that's going to be much smaller than all the other corrections that we're going to worry about shortly in this course, including the fine structure and the hyperfine structure. This is much smaller than all of those things. Okay, now it's also true, of course, that the proton is not actually a uniform charge density, as I mentioned. But whatever you think is a more realistic model for it, you could plug that in. And basically all that would happen is you'd change the potential. And so you'd change this factor by some amount. It might be a more complicated function, but you could evaluate it. And people who do this for a living have in fact done exactly that. Okay, and so that's something you can do. Another thing we can ask is, that was just the ground state. What happens if we worry about some excited state? So remember that in doing this, what we really did is we set the wave function equal to a constant anyway. So we effectively set the ground state wave function equal to its value at where the proton is. Okay, and that's just a constant. Okay, that was this right here. So it turns out it doesn't even matter what the wave function of the electron is doing anywhere except where the proton happens to be, which to a good approximation is just at the origin. So for a general rule, for a general NLM state, okay, all you would do is you would take psi NLM as a function of position squared. You'd replace it by the radial wave function squared times a YLM squared, because that's what the hydrogen atom wave functions look like. And so you would get a correction at first order in the energy for the NLM state, which is an integral d omega YLM squared. Remember, omega, this is just d phi d cos theta. Okay, and the point is, this is all just equal to 1 anyway. Then there's the radial integral, which is it just goes from 0 to a proton. Okay, and then there was our stuff that went here. And then there was RNL of 0 squared, which it turns out is 0 unless L equals 0. And if L is, so it turns out it's equal to 4 over Bohr radius cubed times n cubed delta L0. So that's telling you that just for the ground state, we got a very small number, but this is a 1 over n cubed. For excited states, it's even smaller. So n is really, really small. And so the general formula looks like this. You might worry that for excited states, it would have gotten larger, but no, it gets smaller. Okay, so it's in Rydberg's. And L has to be 0 for there to be any effect at all. And that means M has to be 0 also. So this only affects S states. Remember, S is the code that tells you it's angular momentum 0. All right, so it turns out this is actually of some practical interest because there's been some controversy lately about it. Okay, so there are 2 different ways that you can try to measure the proton radius, and you have to be careful how you define it exactly. But there's one value that tends to give things like 8.76 times 10 to the minus 16 meters. I'm not going to write down the uncertainty because they keep changing. And this is from electron-proton scattering. So that's not what we've done here. And then there's measurements that do just what we did here, and they get a lower value, about 8.32 times 10 to the minus 16 meters. Now, when I say they did exactly what we did here, actually they do everything we just did, except they replace the electron by a muon, which you can do because the muon and the electron have the same charge. So this is actually from muonic hydrogen. So you just have a proton and you let it capture a negative muon, and you measure the energy shift between states, and then that gives you a proton. Of course, they also model the proton charge density a little bit more sophisticated way. And I didn't write down the uncertainties, but it turns out they're small enough that it's not obvious what's going on. Okay, the reason you use muons is because the Bohr radius for a muonic, I'll write it like that, a muonic hydrogen atom is the normal Bohr radius times the mass of the electron divided by the mass of the muon. It just goes like 1 over the mass. And so that means if I look at this formula, I'm going to be replacing, if I use muons rather than electrons, I'm going to be replacing the denominator by a much smaller number, which means this is going to be about 40,000 times larger. That's why they use muons rather than electrons. So anyway, I think nobody really understands completely what's going on here. There have been different experiments claiming different things. This is called the proton charge radius puzzle. There have even been people who claim that maybe this is telling us something about quantum gravity. Words cannot express how silly I think that is. But in any case, there's still a little bit of controversy about this. And so it'll be interesting to see what happens. My guess is it's just some subtle difference in the way that the A sub p is defined for different experiments, but who knows? All right, that's it for today. Sorry, I went a little bit over, but I did want to mention that interesting application of this sort of thing. And let me ask if there are any questions on today's lecture.
This last phenomena you just presented, is this in any of your references? Would you have any recommendations on papers or books on this?
I don't. It's sort of a current event. And so one reason I didn't put it in the notes was I was afraid it would be obsolete by the time you read it, which it might well be. So there's several different experiments that keep measuring this, and they're going to keep measuring it until they come to some resolution. And so I guess the best thing I could recommend is to Google proton charge radius puzzle. And I wrote this down probably a few months ago. So it's possible that even these numbers that I wrote down are now obsolete. I haven't actually checked within hours. So
Do you think if they figured something out like this, they figured this out, it would be Nobel Prize worthy?
I strongly doubt it unless it turns out that there really is some weird new physics thing going on, which I'd be willing to bet a lot of money is not true, but who knows?
I see. Is the discrepancy just so small that it doesn't really matter for most things that we use it for?
It doesn't really matter except that it's a probe of what's going on at fairly short distances. Now, the thing is, we've also done lots of other probes of things going on at short distances. For example, at the Large Hadron Collider. And so naively, you would think that if there were some weird new physics thing that was affecting this compared to that, we would have seen it in some other way. But who knows, right? So my guess is it will turn out to be something mundane, and or it will just turn out that one set of experiments is wrong and the other one's right. That can happen. But I don't really, I'm a theorist. I don't have any special insight into these things. That's just my guess. Other questions? All right, let me stop.
If you ever happen to come across any updates on this, will you let us know?
Yeah, sure. I mean, I'll see if I find some updates on this.
Thank you.
Sure.